Good morning or good afternoon, everyone, and welcome to today's event, End Drift, Boost Performance, Real-Time Airflow Optimization for Coal-Fired Power Plants. We're pleased to have with us today Hans Conrads, Founder and Chief Executive Officer of Promicon GmbH, based in Barleben, Germany. Promicon provides digital online flow measurement systems for novel applications in thermal power and industrial measurement and control processes. My name is John Evans from Krishnan and Associates, an energy industry marketing firm, and a sales and marketing partner for Promicon, and I will be moderating this webinar. Our topic today specifically addresses drift-free monitoring, providing real-time and accurate gas flow measurements using Promicon's Nikon Air technology, essential for maintaining efficiency and reducing emissions. During the presentation, feel free to submit any questions that you have by clicking on the Ask a Question box at the bottom of your screen. We will address as many questions as possible at the end of the presentation, and we'll answer questions at a later date that we don't get to. And now, please allow me to welcome and introduce Hans Conrads, CEO of Promicon. Hans received a master's degree in electrical engineering from the RWTH in Aachen, Germany, and subsequently he founded Promicon. He has invented numerous measurement systems for the power, cement, and smelting industries, and today these measurement systems are installed in hundreds of plants around the world. Hans is the author of numerous patents and many conference papers on process measurement of gas and solid material flows. Without further delay, we'll now begin, and I'll turn the presentation over to Hans.
Well, Bob, thank you very much for the kind introduction. I welcome everybody who is participating in today's presentation, and I'm happy to talk about the optimization of power plants by better airflow measurement. I think we all know the problem that in many cases in combustion, we have issues in the boiler, in the unburned carbon, in the NOx, but we don't know really where it's coming from. And a very big culprit of this is usually the airflow or the gas flow through your boiler. So today I'm happy to talk about ending drift in measurements and boost performance. I will be going over the technology as well as the applications. So let's have a look. Before we start, just a very brief one on my company, Promicon. We have been around since 1995. In fact, our company, this year, we are celebrating our 30th anniversary. We're located in close to the city of Magdeburg, which is about 1 hour west of Berlin, Germany. We have developed measurement technology for power, cement, waste to energy, and smelter industries. And everything that we invent is actually has the purpose of measuring gas flows, process gas flows, in order to optimize the thermal process. So with our products, you can definitely have a better and safer operation, you save energy, and also you leave a smaller environmental footprint with your plant. The main industries that we serve are power generation, waste to energy, the whole area of steel manufacturing, and cement making. And then we also have some other industries. We're into limestone, lead, zinc, copper, so basically non-ferrous metals, and even the glass industry. For our main three markets, power, steel, and cement, you can see what kind of projects we've been doing over the last 30 years. You can see the main focus here is clearly Europe and North America, although we do also have quite a few installations in Asia and in South America, as well as Africa and South Africa. So let's talk about digital and drift-free vector airflow measurement three things that I would like to explain. What is digital? What is drift-free? What does vector mean? And why is it important for your plant? First of all, let's have a brief look of where you can measure in your plant in order to optimize your boiler. Every boiler, of course, has an air intake, and the air intake, or fresh air intake, is used to route the air after it's preheated to the mills as primary air, or to the burners as combustion air or secondary air, including the overfire air, the OFA. What else can you measure? Of course, in the boiler, you also find gas flows after combustion. These would be flue gas flows out of the air heater, flue gas flows into the precipitator, or out of the precipitator into the ID fan, or into the scrubber units. Air flows and gas flows are the main transport devices for energy in and out of your boiler. And that is so important because a boiler is a very large machine, and it is very important where the air enters the boiler and also how the gas flow gets out of the boiler into your flue gas cleaning systems. And it is very clear, very obvious to many operators that the air flows and gas flows are a critical component for the combustion performance. So why is it so difficult to measure air into the boiler? Actually, airflow has been measured for many, many decades. It has been measured for 100 years or even longer. So why is it so important and why is it so difficult to measure airflow into a coal-fired boiler? Let's have a look. The reason is because the airflow is a process gas. What do I mean by process gas? A process gas is typically a hot gas that contains dust when it comes to thermal processes. And it's not very easy to measure process gases, and it's very hard to measure them reliably and drift-free over longer periods of time. So when it comes to air that goes into the boiler to transport coal to the burners or to oxidize the coal in the burner, when it comes to primary and secondary airflow, why is it so hard to measure these airflows? Well, the answer you can see in this picture. Every larger boiler has one or usually two of these rotary air heaters. Some big boilers even have four, two for primary, two for secondary. And what do these rotary air heaters do? They basically push the heat that gets out of the boiler with the gas flow back into the boiler. So you have your flue gas leaving your boiler at, let's say, 800 degree or 850 degree Fahrenheit, and it then goes into the air heater, which is basically a carousel with a huge amount of little metal plates that are heated up by the flue gas. You can see this in this picture by this red arrow. Flue gas is coming down through the air heater and it's heating up the plates, and by that it's losing a lot of its thermal energy. So when the flue gas gets out, it's about 300 degrees Fahrenheit or even less. So these heated plates now slowly rotate into the other section of the air heater that you can see with this blue arrow, and the fresh air coming through is heated up by the plates. So the plates are basically pushing the heat back into the boiler by moving the heat from one side of the rotary air heater to the other side. And the cold air, which is basically the fresh air taken in by the SD fan, is then passing by these plates and picking up the heat. So far, so good. Of course, these plates are also picking up something else. They are picking up the fly ash. They are picking up the fly ash that sticks to the plates when they rotate through the hot side, the flue gas side. So the flue gas, with all its fly ash, is not only giving the heat away to the plates, but also a considerable portion of its dust and fly ash. And this fly ash is then transported onto the cold side, where it's taken away by the cold air, and so the whole ash reaches the boiler, the mills, the burners, with the preheated airflow. So we can basically say all the airflows that go into the boiler as soon as they're preheated by a rotary air heater, they carry a lot of ash. And this ash is it's just by coincidence, but it has a negative effect on the machine itself. The ash can be abrasive. The ash can also lie in the bottom section of the ducts. But most of all, the ash is impacting the ability to measure the airflow itself. And why that is a problem, we see on the next slide. The next slide shows you a typical arrangement to measure airflow into a boiler. It's a very old principle of measuring airflows. It goes back to a very smart physicist, I think it was a Swiss guy, by the name of Mr. Bernoulli, and he detected that if you have an obstacle in a large air duct and the air is accelerated by this obstacle, such as a venturi, then the airflow will be proportional to the square root of the delta pressure over this obstacle. So you have, let's say, a venturi. You have two pressure points, one before the venturi and one inside the venturi throat. And if you measure these two pressures, the static and the dynamic pressure, the dP will be an indication of your flow in a way that the square root of the dP is proportional to airflow. Very simple principle, very elegant, and works very, very nicely. However, in the coal-fired power station, it's different. In the coal-fired power station, you get a problem. And the problem is the fly ash that I just mentioned. The fly ash tends to clog the impulse lines that are needed to transport the pressure from the duct to the dP transmitter. So you can see these impulse lines, one for the static, one for the dynamic pressure, and just assume that one of these impulse lines gets blocked. Why do they block? The ash creeps into the impulse lines over thousands of hours. The ash can get pozzolanic. The ash can fill up this impulse line and basically block the impulse line. It can block it so well that sometimes it is even blocking the complete pressure. And if that happens, nobody in the control room notices that. And I will explain in a minute why that is such a problem. But let's first look at the primary effect. The primary effect is that your dP transmitter is not measuring dP anymore. dP stands for delta pressure. And it's very important that the two impulse lines are both open because you only want to measure the delta, so the difference between one leg and the other one. If one leg is blocked, what will happen is that one leg, the free one, sits on 1033 millibar plus the static pressure, and the other leg is undefined. So you will not see your typical 20 millibar or your few inches of water gauge in delta pressure. You will see a different pressure which depends on changes of barometric pressure outside your plant. You can see 20 millibar of pressure is not very much as compared to 1,000 millibar. Yeah? We're talking about 2%. So if you have, for example, a thunderstorm coming and your barometric pressure goes down from 1,033 millibar to 1,000 millibar, all of a sudden your full scale delta pressure is already used up. So you really have a big drift in your signal. Your signal is not showing what it should show, but it's showing a deviation of 50%, 30%. You get big deviations with changes in this delta pressure by clogging or by blocked impulse lines. A very, very important thing. And the question is, what does your operator do? The question is, does your operator even see it? Does your operator even have the chance to see it? And the clear answer is no. Your operator usually can't see these effects because your dP transmitter is hooked up to a controller, to a DCS system. And the DCS system is controlling your louver dampers. And it controls the louver dampers so that the flow that goes into your boiler reaches the set point again, right? So in your DCS, you have a certain set point, let's say so many pounds per minute of air. And if your delta P transmitter is drifting, let's say it's drifting down, then the louver damper opens up. And it opens up so long until the measurement value of the DP transmitter reaches the set point again. That's what some people call a self-fulfilling prophecy, right? The controller basically forces the louver damper into a position where the DP transmitter shows in the value that the DCS system is expecting. So your operator sits in front of the screen. He sees, let's say, 6 mils, and all 6 mils show an airflow that's pretty much the same, or that's pretty much what he expects. But what he is actually seeing are 6 set points. He doesn't see a true measurement. Let me show you this in another picture, what I mean by that. Right, and what this practically means, we can see on this slide. This is from a power station in Berlin. It's a coal-fired boiler, and it has 16 burners. And what you can basically see here is the secondary air to one of these burners. And the dark blue line that you can see is the secondary air measurement by delta pressure. Now, when you look at this line, you can see that it's more or less divided into two. On the left-hand side, it is a bit noisy, and on the right-hand side, it's much more smooth. What happens in between is basically a large gap where someone cleaned the impulse line and therefore made a much better transmission of the delta pressure to the DP transmitter possible again. So you can see the noise of the left side is gone on the right-hand side. However, the level of the measurement, which is 25,000 cubic meters per hour, that level has not changed. There is no change in the level of flow. But if you look below to the damper position, that light blue line, you can see that not only the noise gets less, but the level of the damper completely changes. So before and after cleaning, the damper has a different position. What does that tell you? It tells you that the flow must have changed because the damper has changed radically. However, the operator could not see that the flow has changed. And that is exactly the point. The set point is 25,000 norm cubic meters, and the DCS system will always control the damper to reach that set point. So the operator is looking at 16 burners. He sees 16 times 25,000 norm cubic meters, and he basically thinks that he is fine, but he is not. And the deviation that you see is not 1 or 2%. This is massive. This is really a big change. We see 10, 20, even 30% difference. Now imagine what that means for your burner. Imagine what that means for your mill. If you have 20% airflow too high or too low, that's massive. So let's look at one other. This is another example. It's from a very modern boiler. It's an Alstom boiler, T-fired, 800 megawatts, ultra supercritical, with all the bells and whistles. And also, this boiler has an air heater, a single air heater, largest air heater in the world, and the same problem. You have congested airflows, and look at that red line. The red line is the DP. Now, it goes in a straight line, and it starts to be very noisy until someone goes out and cleans the impulse line. And after that, it's very flat again. However, before and after cleaning, same level. But not so the air damper. The air damper is the blue line. And on the blue line, you can clearly see before and after cleaning, 2 different levels, quite radically different levels. So this is a common problem that is very, very hard to detect. The yellow line below is our Promicon measurement, which follows the damper pretty well because our measurement does not drift. It always follows the true airflow. So that is one of the main problems in secondary air. I would say in every boiler in this world that does not have digital airflow measurement, you will have problem with one or the other airflow measurement. There's not a single boiler without this issue. And some boilers have dozens of airflows that are not correct. Here you can also again see the typical drift, the typical problem that comes along with drift, and that's this noise. We were talking about the noise. Why do we have noise when the impulse lines get clogged up? We have this noise because some of the impulse lines are very long. They go over many feet from one burner deck to the other where all the DP measurements are lined up. And if you have such a long impulse line, then the change in delta pressure in a blocked impulse line will be transmitted very slowly. And you can see this very nicely when you have an analysis of the damper opening and the delta P. Those more or less sine waves that you can see are offset by nearly 90 degrees. So they are in perfect resonance condition. And as soon as you clean the impulse line, this is gone, and also the drift is gone. So that is the biggest problem. You do not have a stable and a drift stable signal. Another problem that I mentioned is we measure a vector. Why is a vector important in measuring airflows in power stations? Have a look at this one. This is a manifold of a combustion engineering boiler in South Africa. You can see on this one that the bulk air duct, which is the blue rectangular area on the bottom of the picture, this bulk duct comes more or less towards you. So the airflow comes more or less out of your screen that you see. And then for the middle manifold, the airflow bends upwards. So it turns by 90 degrees. And therefore you can see it goes up, but there is no swirl. It goes in a straight line. Now have a look at the manifold left and right from that. You will see the air does not only have to turn upwards, but it also has to turn sideways. It has to turn left, and then left again, and upwards. So basically, what this motion describes is a sort of a screw-type movement. Now, as the air has a mass and an inertia, it does not want to follow this, so therefore it starts to screw counterclockwise or counterwise. It spins. And that swirl can be easily seen in this CFD simulation. So the two manifolds left and right have a very strong spin in opposed directions. Why is this a problem? Any delta P measurement or any thermal mass flow measurement is a scalar measurement. It only measures the value, delta P or delta T. It doesn't measure any direction. And if you have a strong spin in your flow, the measurement is simply wrong because the spin adds to the air velocity, but it does not add to the air mass flow through the duct. That's the very big difference. The air velocity gets larger by the spin, but the air mass flow through the duct does not. And that's a big problem that our measurement does not have, because our measurement measures an air velocity vector, and the vector has a direction. We only measure the air in the direction of the duct. We don't measure the air velocity as an absolute value, but as a directed flow. And that is another very big advantage of our measurement, because you never know how much swirl you have. It does not come necessarily from a fan upstream. The swirl simply comes by the fact that air ducts turn in different dimensions. They turn up, they turn sideways, and therefore you get these movements of air, and it's usually very hard to stop them. You have to put in a honeycomb, a flow straightener, that costs you a lot of pressure drop. Our measurement is not sensitive to this. It only measures the flow in the direction of the duct, and therefore our measured airflow is really equal to the air mass flow. Okay, so I've talked about our magic measurement. Let's have a little bit of a look at why is this so much better, how does it work, what do we do differently than other measurements of gas and airflow? Basically, we have a correlation-based measurement, and the correlation is done basically by a digitized signal that we get from our sensor. So we have a signal, we digitize it, and the digitized signal goes through a digital correlation algorithm. So it's all a digital measurement that is not prone to any drift or not prone to any deviations over time. And I will explain exactly how that works. The other thing is the signal generation basically is done by an electrostatic signal that we get from the gas. And let me explain how that works. If you have a duct, you can see the two blue lines that are sort of describing this duct here. You put our sensor in. Our sensor is acting like an antenna that can pick up electrostatic charge. Why do we have electrostatic charge? We have ash particles going through the duct, and these ash particles are always charged if you have a hot gas. Where does this charge come from? The particles have friction against the gas, against themselves. These small particles have a huge surface, so that surface charges up. I wouldn't say it's exactly like in a thunderstorm, but it's a similar mechanism. So you have these charged particles going by the antenna, and if the particles are slightly charged positive, the antenna will have a negative charge called Coulomb's law. So the total sum of all the charge must be neutral. But as this cloud of positive charges moves by, another cloud with a different charge arrives. So you basically, as these particles go by the antenna, you will see an electrical current on our antenna because the charge changes over time. And this electrical current is very unique over time. We call it a fingerprint. We call it a time signature. It's very specific for this moment in time. And when you look the next second, the signal will have a completely different look. So every second, every millisecond, the signal changes. Yeah. So the question is now, if you have two sensors and you put them behind each other in a very close distance, about 1 foot, about 300 millimeters, what will the signals on these two sensors look like? And you can see that if these sensors are close enough, over each second, the signals will be very, very specific. But since the one sensor is very close to the other sensor in the flow direction, you can see the signals are very similar. The signals do not change from one sensor to another sensor within a few milliseconds. So if you put these two sensors close to each other, you will see that you get two signals that are really similar. However, what you can also see, they're time shifted, which is not a surprise because the sensors do not sit on the same spot. One sensor comes first and the other one sensor comes last. So the delta T that you can see here can be calculated by a so-called cross-correlation. What the cross-correlation function does basically is it measures the overlap of the two sensors, right? So you have an overlap of sensor 1 and sensor 2. And if you measure the overlap and then you shift the signals towards each other in time, then the overlap will be different. And at one point, when the signals basically overlap perfectly, you will have this maximum in the cross-correlation function. And the time that you can see in this cross-correlation function is basically the flight time from sensor 1 to sensor 2. So by doing this cross-correlation, you can calculate out of these two raw signals at which time shift do we have the maximum overlap. And this time shift is our time of flight. This is very, very fundamental because that is your drift-free measurement. There you have it. Every second, our system will give you a time shift. If you now take the distance of the sensor and divide it by the time shift, you get a velocity. You get feet per second. Yeah? And if you now multiply with the cross-sectional area of your duct, you will get cubic feet per second or cubic feet per minute. You already have your actual flow. So if you now correct that actual flow by the gas temperature and by the barometric pressure outside of your power station, you end up with your STP flow. And that's it. So the measurement is very, very simple. You have a box, you have two sensors. The box gives out a velocity reading, and your DCS system multiplies that velocity reading with the cross-sectional area, and it compensates for gas temperature and barometric pressure, and there you go with your STP flow measurement. Why is this so important? It is so important because this measurement will not drift over the lifetime of this system. So if you put the system in and 10 years later, you look and check the calibration, it will be like on day one. And that's simply because we are only measuring time shift. We're not measuring anything else, right? The electrification that we measure, or the current, is only a timestamp that we use. We don't care about the current itself. We don't care about the strength of the electrostatic signal. If that strength is twice as high, it doesn't matter, because the only thing that is of interest to us is the time shift between signal 1 and signal 2, nothing else. Yeah. For the engineers amongst you, if you derive both signals by time, so you make a delta signal over delta t for both signals, and you do the cross correlation, you get exactly the same time shift, because all we are measuring is our events over time. We don't care how big the signal is. And that has a huge consequence. If the sensor gets dirty, if the sensor has some issue, if there's some problem, you will never see a different value. You will always see the same value because the time shift does not change. The time shift is always constant. So the consequence out of this is that the system is installed in your plant, and then you forget about it. And it's the same for primary air, for secondary air, for OFA. You will never have to climb up to the sensors and do traverse measurement and double check. That's negligible. You don't need that. And think about how many measurements you have in your plant. You have 20 measurements, 30 measurements, a lot. And none of these measurements you will ever have to recheck. One other thing that people frequently have to recalibrate for is for zero, right? If you have a delta P measurement, your membrane needs to be zeroed correctly. Now, for our measurement, zero doesn't exist, yeah, as you can see. If the gas velocity goes down, the time shift gets bigger because the gas needs a longer time from sensor 1 to sensor 2. So the more you go down, the larger the time gets. And at velocity 0, the transit time is infinite. So there is no 0 point that we can measure, and therefore there's also no zero correction that we have to do. The measurement principle is very simple, and the simplicity of it is basically the beautiful part. There's no complex things. There are no fancy purge system, no fancy cleaning systems, no fancy correction factors. This is all dead simple. It's a velocity, a cross-section, and a temperature and pressure correction, and that's all. But I promised you something more. I also promised you talk about swirl and why, for us, it doesn't matter whether we measure velocity or we measure the mass of the air. It's the same thing. Look at this picture here. You can see that the two sensors are mounted perpendicular to the axis of the duct. And that means that the distance between the sensors is parallel to the duct. And the distance is important because I mentioned delta P and delta temperature measurements are all measuring only scalar values. Now you might say, well, time shift is also a scalar value. There's no direction in time. That is correct, but we measure distance over time. And the distance is exactly the vector between the two sensors. And that's the whole thing. Yeah. If the air, like you have the orange arrow here, that's the airflow, or maybe you have like a swirl going through the two sensors. The sensors don't care. The sensor only measures two time events, and the system calculates with the distance vector between the two sensors that is perpendicular on the sensors. So any lateral air velocity will simply be ignored. The system does not measure lateral airflow. Whereas all other systems, the Venturis and the Pidos and all that, are affected by lateral airflow heavily. So another big advantage. Or here, we look at that, we have the typical swirled airflow between the two sensors. This swirled flow does not affect our sensors because the distance vector between the two sensors is perfectly in line with the axis of the duct. So in this case, no impact. Okay, so that's that. Another thing I would like to mention about the function of our system is what do we do if we have no dust? That's a frequent question that is asked. Let's say our system has no dust. So you purge a mill with cold air. The cold air has not been going through the air heater, and therefore there is not much air, not much dust in the air. For this, we have developed the so-called range extender. The range extender is basically another rod that is installed upstream of our airflow measurement. And this range extender generates electric pulses that ionize the air with a small corona discharge. If you have this range extender in the gas, what you will see is that you have ionized air clouds then coming from the range extender. Why are these ionized air clouds important? Because they induce an electric current on our antennas, like the dust, same thing. So you have an electric pulse sequence, and it's very advisable to have a non-periodic sequence, so you also have a non-periodic cross-correlation as a result. And if this sequence passes over the two sensors, you can see the sensed current. And if you correlate this, you get the same cross-correlation result. Let's have a look. Two sensors. On the right-hand side, you can see two diagrams. The upper one, red and green, these are the two sensed ion pulses, and the blue one is the correlation of the two. And you can get a very nice time correlation again. So this helps you to measure when you have no dust. This is why we call this range extender. We had a certain amount of dust minimum level for our gas, like 800 micrograms. But with the range extender, that level goes to 0. We can measure absolutely clean air up to very, very dust congested air up to hundreds of grams per cubic meter. So we can measure nearly in all dusty and clean gases at the same time. Another reason why we call this range extender is that we found it also extends the minimum flow range that we can detect. So usually starting with 7-8 feet per second, that is now the lower limit that we can measure. And in big contrast to a delta P measurement, our measurement is strictly linear, right? So our measurement is linear from the top level to the lowest levels, which is gives it a very big turn down ratio. And that's something that needs to be discussed a little bit more. If you have delta pressure readings, then it's very hard for you to measure the low range accurately. Because if you, for example, go down to 10% of your max flow, you are talking about 1% of your max pressure, right? And that really gets into into a very, very small pressure measurement range. So DP measurements will show you all sorts of readings. Sometimes they will even show you negative readings. Because in this very low flow range, your pressure is almost 0. So it's very hard to detect a correct pressure that you can then translate into an accurate flow. You have other measurement devices such as thermal mass flow anemometers. They have the opposite problem. Thermal flow meters are very, very good at low range. They're excellent at low range. They have a very high turn-down ratio, but also they are not linear, and they are getting very bad at high flow range. If they are a little bit dirty, or if they have a little bit of a drift problem because they drift, their major drift is at the high end. Now, again, many people believe that if they don't see the measurement being noisy, but it's more continuous and more following nicely, that the measurement is accurate. But that's not the case. Especially thermal mass flow anemometers appear to be very smooth in transmission, but especially at the high end, they can be awfully wrong, because the high end, they don't measure very well. They measure the low end very well. So here in our measurement, it's completely opposite. We have a digital flow, it's linear, and at the high end and the low end has the same accuracy. It will not degrade in accuracy. Here you can see such an example of a range extender as it is installed in a duct. Now, just a few things. How does this thing look like when it's installed? What you can see here is basically the setup that is usually used in a power station. Excuse me. You have two sensors that go to the air box. The sensors carry the raw signal to the box, and the range extender is installed upstream, so you can measure the flow with an ionized gas if there's no dust. You can also see a temperature measurement device installed here. We recommend that this device is installed directly not connected to our box, but we recommend to connect it to the DCS, where you also have your barometric pressure and the geometries of your duct. And the big advantage of that is that you have all these specific parameters, such as area of your duct, temperature of that duct, as well as pressure, that you have that in your DCS. So there's no programming necessary for our box. Our box only gives you velocity, that's it. So you can change our box from measurement location to measurement location without reparametrization. The box always holds the same parameters. There's absolutely no problem. Therefore, we recommend that you only have the sensors hooked up to it. The power supply is usually anything between 65 and 240 volts AC, 50 hertz, 60 hertz, or you can also have 24 volt DC supply. That's up to the user to decide. And then that's basically the whole setup. So for every measurement location, you get a 4 to 20 milliamp signal for the velocity that you then scale and compensate for the individual parameters on the duct. And then you have error levels below 4 milliamps, starting from 3.6 milliamps down. You can have several error level indications: sensor cable broken, sensor reading not valid. 0 milliamp, of course, is then power failure. So these sort of error levels you can then also take into your DCS and use for controls. So summing up why our measurement brings you significant advantages: it's digital. It will never fail on you in drift, never, over the whole lifetime of the system. It measures the airflow in a direction. So it does not measure some airflow or some wind around the sensors. It measures where the air is going and at which velocity is going in that direction. Whether the air is spinning or whether the air has a lateral component, it doesn't matter. The big advantage over the current measurement that you have is, of course, that we do not need any analog signals or anything that can affect our measurement. And the output of our measurement is strictly linear. So you don't have to worry about the low end or the high end. Within the measurement range that we give you, our measurement will be correct. What's the measurement range? I already mentioned that we could go down to 8 feet per second to start, or 6, 7 feet per second at the very low end. At the high end, there's actually no real limitation. Our velocity measurement is not tied to speed of sound or something. You know, we could even measure transonic speeds with this. But of course, for power station applications, it's usually the typical would be 100 feet, 120 feet per second, or 150 feet per second, whatever is desired. But those velocities are absolutely common for us, and we can cover them. Why are these high velocities important for you? Because very often people have an existing venturi, they have an existing airfoil, and the gaps of the venturi or the airfoil are very good measurement locations because they act as a perfect flow straightener. Right? So if you have an existing airfoil, existing venturi, to put our sensors in this location is really helpful. And then, of course, in these locations, you have very high air velocities. You can have air velocities up to 150, 160 feet per second. So therefore, we have this high scale and made that possible. Let me show you a couple of examples of retrofits, because most of you who will be listening will not be erecting a new coal-fired station. In the US, I guess there's no construction, but the fleet that you have will be needed in the future as well. So there is certainly a life, and most of your plants will modernize. And let's look at some of the typical modernization examples. I've shown you a picture of a trend that is drifting from the Alstom boiler. I guess you remember this picture of the 800 megawatt Alstom boiler. This is a boiler in Germany. And you can see here the original venturi. It's not a real venturi, but it's similar. And that has been failing. You can see on the right-hand picture from the outside, the installation, and on the left-hand picture from the inside. So what we have done is we went into the shallow section of this duct, and we installed 2 sensors. And then before the sensors, we also installed the range extender. And from the outside, you can see the range extender as well, the box, and the 2 sensors. And we have been using the system for many years. And the system, again, never been recalibrated, never been maintained in such a way. The only maintenance that they have to do, the system is a so-called SIL2 rated system, so it's a safety integrity level 2 system that is mandatory in Germany. So every 2 years they have to do what they call a proof test, and this proof test is basically switching our system off and switching it on again, and that's basically all we do. Then the system checks itself and it comes back online correctly, then everything is fine. So we could say no maintenance actually, only regular checks. That's what we would recommend. If you have a boiler outage, go through all measurements and check if there's any visible damage to the cable, to the sensors. Pull the sensors, they're still looking good. But if they do and the system comes back all right, then you are fine. It's a digital system. There's nothing else to do. Here's another example. That's a Mitsubishi Hitachi boiler in Duisburg. Here the system was planned in from the beginning. Why do they still have a venturi? Well, it's a very new technology for them back then. And they said, we will put in a venturi because that's the major work, but we will not put in a delta pressure measurement. We'll put the Promicon system in. But if it fails, then we might fall back to the delta P. I mean, that's redundant thinking of engineers. But needless to say, the system is still working today. It came in 2008, so now we have 2025. Still working, customer very happy, absolutely positive reference, like all of the ones that we have done on airflows. Another example that I've not been talking about much, and I'm not sure in how far it is of interest to you, but many power stations also are suffering from back-end gas flows. What are the typical issues? Typical issues would be the flow of boiler flue gas on the left and the right-hand side of the flue gas duct. So you have an A side and a B side. You have two EPs. Is the flow through these two EPs the same? Very often it's not. Very often you have an ID fan, and both ID fans show you the same power rating. They show you basically the same power consumption. But basically the operating point on the fan curve is not identical because one system is different from the other. So one side pulls more gas flow than the other one. Why is that a problem? Of course, the side that pulls more gas usually has the bigger particulate emission problem because the separation of particulate matter is not so easy if you have too high gas flows. So here you can really balance those. Another typical application is if you have, let's say, two boilers and three scrubbers, are all three scrubbers getting the right amount of flue gas? Or is each scrubber getting the correct amount of flue gas? And is it really in line with the amount of line that we're spraying in, etc.? So there's also a good reason to measure flue gas ducts. And here you can see a typical example of flue gas measurement. ID inlet flows, that's what we usually do. And yeah, in this case, it was fairly okay, but we have also seen ID fan flows, which are different by 1%, 1.5%, or even 2%. And for a total gas flow out of the boiler, 2% is a lot. That's not a small number. And we've been helping a lot of power stations around the world to optimize their flue gas flow out of the boiler. As you can see here, a typical problem. You have the air heater out left side, air heater out right side. A little bit hard to see. The left and the right side, the blue and the red, and they are not really on top of each other. So we sometimes see differences in those flows, and that is usually an alarm for the customer. Is one of the sides pulling more ingress air? Ingress air is a big problem after the air heater, or are both sides okay? So it's a good indication also of maintenance requirements of your flue gas path. These are a couple of the applications. I'm sure there are more applications around the power stations, but I think these are the most important ones. And yeah, I think that brings me to the end of the presentation. I thank you very much for your patience, and I thank you very much for your attendance. And if you have any questions, why don't you put them forward now? I'll be happy to answer a few of them. If there are a lot of questions, then we'll answer the rest via email. And yeah, looking forward to further discussions with you. Thank you.
Excellent. Excellent, Hans. That does conclude the formal presentation. We did get questions that came in. They're continuing to come in, and we'll address them in the time we have remaining. As Hans indicated, we can respond by email to any questions that we don't get to. First question, how do I know whether or not I have inaccurate measurement of airflow?
Yeah, I think this is a very, very good question and a very important one. In my presentation, I've already made some examples of implausible airflows. I've shown that the damper position changes when you blow out your impulse line, but the airflow stays consistent. That is a very typical example of a problem. Now, of course, if someone looks into a single reading, you don't know whether the impulse line is blocked just right now, or if that happens next week, or so it's not easy to see on the spot. Let me give you a couple of probable test scenarios that you can run in your plant that are not so difficult. Let's start with secondary air. If you have secondary air, what you have to do is you have to look over the airflows over time. It's very important. You have an airflow trend. Let's say you have 20 burners. You take an airflow trend over 24 hours, and you put the airflow trend on one screen together with the damper positions on the same screen. Now, the first thing that you can see, Are the damper positions similar to the airflows? Usually, if you have, let's say, 20 secondary airflows, you will see 20 times the same value, or even windbox flows. Yeah, they're all the same value. The dampers are usually completely different in value. That is already suspicious. It's not a proof that you have a problem, because each damper could be sitting on the axle in a different angle. But if over this time, over 24 hours, over weeks, over days, you see that some dampers start to be moving around and the associated airflow is not moving around, you can be very sure that you have an issue. I mean, that's a very safe indication. On pulverizers, it's even much easier. On pulverizers, the coal can help you to detect that, because the coal carries moisture. And if we have, let's say, 4 bunkers or 6 bunkers, and they are filled with the same type of coal, then at each minute, your mill should be evaporating the same amount of water per ton of coal, which is grinded. So what you do is very simple. You look at, let's say, 6 mills. For each mill, you get the following values: coal feeder, airflow, temperature in, temperature out. This is 4 values, right? If you now multiply the airflow with the delta temperatures, you basically have a value that is proportional to the amount of enthalpy that is removed, or the evaporation enthalpy that's removed from the coal. If you then put that into relation to the tons of coal that you're looking at, then you get to a number that should be pretty much the same for every mill. Yeah? The mills should not be radically different. Sometimes they are a little bit different if they are running on radically different loads. But if they're similar load or the same load, that number must be very, very similar. Because it means that the same amount of heat will remove the same amount of moisture from the same coal. And if that's not the case, well, physics is the same in all the mills. So where's the flaw? Where's the thing? And well, usually it's a flow measurement that's not working correctly, and most of the time it's an airflow measurement that's causing you the problem. So these are the 2 methods, and what I can only invite you, if you have questions about your boiler and your air, and you have really interest, you could do a couple of screenshots, as I just mentioned, either the trend of the airflows and dampers for secondary air, or the values that I've just given you, feeder, airflow, and delta T over your mills. And you can send us those screenshots, and we can do the analysis for you. It's a little bit of typing into an Excel spreadsheet, but it's not so hard to see where the problems are. And this is usually what your operators cannot look at, because they are busy with so many other things, and therefore it's hard to see. But I think if you look out for it on your plant, believe me, you will find something. Usually every plant has issues. So that's that.
Okay, good, excellent. What is the most negative impact of inaccurate airflow measurement in a power station?
Oh, that's a hard. Okay. The most negative one is a boiler explosion. That, I would say, that's the worst of the worst. I've seen it. I've seen boiler excursions, I think they're called, in other countries, not in the US, fortunately, but boiler explosions when you, for example, have very, very bad air staging, or you have even the fire going out and then come back on again. You can have but these are catastrophic events. And usually in a well-maintained power station, even with the analog measurement technology, these should not happen, because you have CO control and you have feedback loops and you have a total O2 measurement. But the far more typical problems that you have, let's start with secondary airflow and burners. Eyebrows over your burners, flame impingement on the boiler wall, difficulties with flame attachment. All these are typical for airflow problems. You blow out your flame, or you shoot the flame too far to the opposite wall. These are all airflow issues. Now, then, of course, everything in the combustion-related area: high airflow, high NOx, low airflow to a burner, high CO, high unburned carbon. Typical issues. If you have the airflows all over the place, then some burners will produce you CO, other burners will produce you NOx. So you can have CO and NOx at the same time in the burner, in the boiler. Then on your mills, typical problems, mill instability. I mentioned the values that you should look at in your mills, the feeder, the airflow, the delta T. You could also look at your mill amps, the grinding amps. If the grinding amps are vastly different at same feeder settings, the bed depth of your coal in the mill has different heights. And that is definitely an airflow problem. One mill is blowing more PA than the other mill. Or airflow, very, very big problem. If the airflow through your mill is too low, you will get coal deposits in your burner pipes. You will have coal lying in your burner pipes. Yeah? I sometimes see power stations where all the paint is burnt off in a coal pipe, and I can tell you had a fire in your coal pipe, and that's usually transport problems because your airflow through the mill is incorrect. So all really big problems, particle size. If you blow too much air through your mill, you have a too high particle size. Right? So that's out of the zoo of problems. Airflow generates most of them in combustion.
Okay, quite a bit there.
Yeah.
What is the maintenance interval for performing maintenance on your system, and what does this maintenance involve?
Yeah, the problem is that many of our clients don't do any maintenance anymore. So they come back to us after 10 years and say, "Wow, one sensor is not working." Well, then the sensor is either burnt or broken, or the cable is ripped or something. There is no regular maintenance on these sensors, but what we, of course, would definitely recommend is that you look at the sensors, you look at the system at every overhaul. So you don't have to go to the boiler house every other day or every other week, check the sensors, blow out lines, all that's gone, that's the past. So I would say maintenance is another very big advantage of this measurement system. Only regular care about your sensors when you have larger overhauls or maintenance cycles in your plant. So that's all, and it's usually a visual inspection. There's nothing to test or you can't recalibrate anything because it's a clock. This airflow measurement is basically a digital clock. That's all it is. Right?
Yes, I see. Does Promicon provide installation and commissioning services? Is this necessary?
Yes, we do. We have American operations, and they provide for the American market both service and installation. If you are retrofitting 20 burners with our measurement, it's certainly advisable to have somebody from Promicon at site and help to get all the signals in, do the loop test, get it all hooked up. We know that clients can also do this by themselves. If they can, that's fine. But if they want our assistance, it's absolutely no problem. And we're happy also to assist in any case of a breakdown or a question. We have local presence in the U.S. for that.
Okay, very good. We have time for one more question, so we'll just pick one. Are changes of the ductwork necessary for installing the sensors?
Okay, another good question. Ductwork. I have not touched upon this so much, but of course, in power stations, ducts are always wide and short. In terms of their length, they always have a huge cross-sectional area. And usually the ducts bend around the corner and then they split, and here's the burner. So you have stratification issues. You don't have much straight run on the duct. So are modifications necessary? On a long duct, no. We just put the sensor in through a couple of openings, and that's it. So also here, what many people fear is flow profile, the typical laminar flow profile. At the velocities that you're looking at in power stations, 10, let's say 30, 40, 50 feet per second, 80 feet per second, you do not have a laminar profile. You have a very flat profile, and therefore you will also have a very accurate reading by just putting the sensors from the outside into the duct by, let's say, 1/3 or 1/4. Sometimes, of course, no, not sometimes, a lot of times, in power stations, you have bends. And behind the bends, you want to measure. Now, in most of the power stations that are existing today, there are some devices installed that usually have an existing duct modification in them. A duct modification would be an orifice, an aerofoil, a venturi, something like that. Now, those duct modifications we like to use because they usually act as flow straighteners. If you have a stratified profile after a bend and it hits a venturi, then in the shallow section of the venturi, the profile will be very flat. The venturi more or less forces the profile to be flat again because the air is accelerated. And the same thing you have with any other obstruction in the duct, with an airfoil or with any other. So if you send us a drawing from these, we can get you a very good installation position, and that usually includes drilling a hole, putting a mounting adapter on, and sticking our sensors into that location. And you could even run the existing venturi or the existing aerofoil parallel. So if you want to do a test, you don't even have to to put our sensor into your DCS before you haven't tested it. You can just put it in parallel, and then you can see how both run parallel. But finally, for the final installation, you can then hook it all up to your DCS, and you will have a very good measurement. So question is, usually there is no big modification necessary in your boiler.
I'd like to thank Hans for today's presentation. We had an excellent turnout today. And I would also like to thank all of you attendees for spending some time with us today. This presentation has been produced and marketed by Webcast Experts, a division of Krishnan and Associates. Please keep an eye out for future events from us, bringing you more information on advanced products and services within the power generation industry. We're finding that today, more than ever, webinars present the ideal forum for communicating technologies, products, processes, and services to widely dispersed audiences. If you have an interest in learning more about our webinars, or if you have subjects of interest for future webinars, please feel free to contact Ravi Krishnan at 1-203-257-9232 or by email at rk@krishnaninc.com. Also, you can contact Luke Rathel at luke@webcastexperts.com if you wish to access any of our previously held webinars that are now available on demand. This concludes our presentation. Thank you and have a good day.